Hello everyone. I welcome you all to this presentation, which is about a novel method of generating targeted cross-site scripting exploits using dynamic data flow analysis. So, meanwhile, I am Sufyan and I'm a computer science master student in the University of Darmstadt. And this is a joint work between me and Tom from SAP Security Research and David and Martin from the TU Braunschweig. And now to the agenda. I will first show you the motivation behind this work. After that, we will cover how tainting in the client side works and how we take advantage of it to modelize the web applications. Then we will present the way we generate the exploits in comparison to other previous methods. And I will then report on our experiment that we did by discussing the results of a large-scale crawl and exploits generation. Okay, so cross-site scripting is a type of security risk that is very relevant. And in the last report, 2017 of the OWASP Top 10 ranking for web application security risks, it is ranked in the 7th place. And actually, injection attacks, which are similar types, are also frequently present in this list. And let's now start by seeing what a vulnerable flow is. And for that, we modelize the application as some data flowing from a source to a sink. The source can be a user-controlled source like, for example, an input or a URL. And the data passes then several functions and lands into a sink, which can be, for example, a document write or cancel log, etc. Now, a vulnerable flow is, for cross-site scripting, is any flow that is coming from a user-controlled source and flowing to a sink that is relevant for cross-site scripting, meaning that a script execution is allowed in this sink. For example, here we have a data flowing from the location hash to a DOM element, which means that instead of the name Christian here, a script tag could be also injected, which causes the execution. Now, I would like to talk about some types of cross-site scripting. And cross-site scripting is, in general, a type of vulnerability that is typically found in web applications, and it allows the attacker to inject client-side scripts into web pages viewed by other users, and it basically bypasses some access control that are present in the browser. And here is a first type of cross-site scripting, which is the reflected one, and it occurs when the vulnerable web application echoes some input with no proper sanitization. And here down is an example where the attacker sends in step 1 a crafted URL to the victim, for example via email, and the victim clicks then on this and requests in step 2 the URL with the payload on it from the server. The server will then reflect the exploit in the HTML and sends it in step 3 back to the victim, which leads to a script execution in the browser. Okay, the second type of which interests us in this work is the client-side cross-site scripting, and it works in the same manner. The only difference is that the response sent back by the server doesn't contain the exploit, and the victim's browser will insert this malicious script into the DOM during the rendering of the page, which triggers then the script execution. And this type of cross-site scripting appeared actually after the reflected one because of the move from the traditional serve of websites to a client-side JavaScript rendering. And some example of functions that allow dynamic change are, for instance, document write, eval, or also some event handlers. Yes, this JavaScript rendering came with much flexibility, but it has also some critical issues. Now, we move to the second section, which is tainting in the client side. Well, tainting is a well-known way to detect cross-site scripting, and here I will talk about it and how we use it. Basically, you need three things to apply tainting to an application. First, you need to identify what are the sources and the sinks. As seen, a source is a user-controlled input, like the location hash, and the sink function is a place where the data is used to control the flow of the program. Once this is done, you also need a mechanism to track the data flow inside the application. And the third thing you need to is to define the mitigation policy, which could be only to detect these flows or maybe also to mitigate them or even to block them. We implemented then these tainting capabilities in a Firefox browser by enhancing its JavaScript engine to propagate taint information for strings. It supports dynamic byte-level taint tracking of suspicious flows and gives us also information about the operations a string went through. Among others, the encoding and decoding functions. Now, the problem that arises is, can every cross-site scripting vulnerability be exploited using a simple payload? And here is a slightly different example where the flow is landing into the attribute value source. And if you try here to use the payload from the first slide, it won't work because a script tag won't execute inside an attribute value. But what you can do is you can first close the context until you reach the top level and then inject the script payload. So it's not easy to find out which exploit to insert unless we analyze the context in which the code is injected. So the idea of this paper is to present a way to generate an exploit using the information from the taint analysis. We present in this work two previous solutions from the literature, and also our solution resulted from this work. And at the end, we compare all these methods. And concerning the scope of this paper, we are focusing only on the flows coming from a location source. Now, in this third section, we come to discuss the process of the automated generation of cross-site scripting exploits. And in this section, the first topic is to define the structure of an exploit. And as stated before, a cross-site scripting exploit is context dependent, which means that the exploit used inside an attribute, for instance, isn't the same as the one used in a tag text file. And an exploit depends also on the usesync method. For example, the document right here allows to insert a script tag and execute it, while the element HTML, for instance, will just insert it without triggering the execution. Generally, a cross-site scripting exploit has the following form. It consists of a breakout sequence, which allows to go beyond the actual context to where a script execution is possible, a payload that contains the function to execute, and a break-in sequence, which comments out the following code so that no syntax error will be caused. And the next topic to define is what are the contexts for the XSS execution. In general, we define 5 contexts, which are the HTML context, consisting of the content and the attributes, and here the browser will interpret the code as HTML code and insert it into the DOM. The second context is the URL context, and it's a special case of the HTML context where the input is injected into a URL attribute like the href or the source. These two first contexts are combined into one category called the HTML element sync. The next two contexts are the JavaScript and JSON contexts combined into the execution sync category. It consists of functions like the eval, which takes the text in string format and interprets it as a JavaScript code. The last context, which is out of the scope of this paper, is the CSS context, and within it, an input is reflected to a value of a style attribute. So, let's see how we generate each part of the exploit, taking in account what we have seen till now. We start by the breakout sequence, and here we use two methods depending on the context category. For the HTML element sync, a breakout sequence consists of a context prefix, a closing current tag, and closing tags. The context prefix is either a hash or nothing, and it has to do with the injection place in the URL, which we will talk about later. We determine the closing current tag by generating a HTML parsing tree for the tainted string and its context, and then traversing the tree from bottom to top. Each context is then closed. At the end of the breakout sequence, we have these closing tags, which we add arbitrarily. The reason is that if we are inside one of these, the payload inserted won't work correctly. For example, the text area doesn't allow a script execution inside it. Let's see now an example of constructing the closing current tag. Here we have the same example as before with the source attribute, and the parsing tree of this example is in the following structure, where we have a root, inside it an image tag, and inside it a source attribute. Traversing this tree bottom up leads to closing the current tag in this way. Okay, now we move to the execution sync, and for the example here we have a function as a string stored in a variable. Within it, we take the hash value and redirect the page to it. Simple example. This is a flow that is relevant for cross-site scripting because it comes from a user-controlled source and flows to the eurosec. The question here is which breakout sequence can be used to land to a place where a script execution is possible. Two solutions here. First one is to get to the block statement. The problem here is that the function redirect has to be called in order to execute the payload. The second solution is to close further the context until we reach the top level, and in this case the advantage is that the payload will be executed even if the function isn't called. So first step is we generate the parsing tree for this code. And after that, we form the breakout by a context prefix, just like in the HTML method, and then the closing current nodes generated from the parsing tree. And here is an example. It's from the last example again, with its generated parsing tree. We then traverse the tree bottom up and close each context. As an example, we can see here that the literal is closed with a single quote, or the call expression with a parenthesis, and so on. At the end, we got the closing tags allowing to get to the top level. There, a payload can be injected. Well, there are some differences between HTML and JavaScript injection. In fact, HTML is interpreted even if the syntax isn't 100% correct, whereas a JavaScript code won't be executed if there exist some syntax errors. Therefore, a last check is done for the generated breakout sequence to assure that its syntax is correct. Now, I'll go quickly over the other exploit parts. The payload consists of entering the script context, which differs from context to context, and then a function is attached to to test the exploit afterwards. Here, for example, an alert to simplify it. The last component is the break-in sequence. It is also context dependent and allows to close the script context and start the comment. Okay, now that we have an exploit generated, the question is where to inject this exploit exactly to increase the success validation rate. In this paper, we are only considering the URL sources, and you can see from the diagram here that the relevant parts for URL injection are the query and the fragment, because otherwise, if we inject the exploit into another place, the URL will be redirected to another location than the one that we are interested in. For this, I'll next present two injection methods from two other works, and then I'll show you our improvement based on the taint analysis information. I will call the first method method A, and it comes from the paper 25 million flows later. It consists basically of appending an exploit to the end of the URL as a fragment. For example, we suppose that we have here this URL and the tainted part is abcd. With method A, the URL will look like this and the exploit will be present in the fragment. For the second method, which is method B, taken from the Domesday paper, it is only relevant when the tainted string is part of the query parameter. What they will do is that they would extract this key value pair and replace the value with the exploit. Then append it to the fragment preceded by an end symbol. Methods A and B inject both the exploit into the fragment in order to not be sent to the server side. For method C, implemented in this work, the objective is to calculate where the tainted part is present inside the URL and then either replace it completely, partly, or not replace it at all. We here don't always make use of the fragment to inject the exploit, and the hypothesis here is that this method will be more precise and lead to more validated exploits. To read more about method C in depth and how we calculate these indices, I invite you to read our paper. In the big section of this presentation, I'll present the results we got from doing a large-scale crawl over 100,000 domains. This is the solution architecture, which consists of a crawler, a generation and a validation service. In addition to them, the taint analysis is done via the taint-aware browser. In the first phase, the web crawler reads the list of the domains and from each domain extracts up to 10 pages from the depth 1 and sends them to the taint-aware browser to be analyzed for suspicious taint flows. The result is then persisted for the next phases. In a second phase, the generation service will generate for each relevant flow an exploit using the methods A, B, and C. And in the last phase, these exploits will be checked using the validation service, which visits then each crafted URL using a headless browser. And here are the results of the crawling phase done in comparison with these from the two previous works. A total of about 390,000 pages were visited, and we collected a total of about 21 million flows, and this corresponds to about 53.6 flows per page, which is approximately similar to the number realized in the 25 million flow later paper and half what the Domesday paper got. And between the crawling phase and the generation phase, we have done some pre-generation filtering in the same way done in the two previous works. So we eliminate the non-relevant and the redundant flow, and we also exclude the flows containing an encoding operation without any subsequent decoding, as we know that our exploit won't be effective in this case. And in total, out of 21 million flows, only 15,710 were the suspected ones. And for those, we generated the exploits in the second phase. And here are the results of the generation and validation phases. And here is to note that we ran 3 methods on the same dataset. With method C, almost 46% of the relevant flows could be successfully validated, which represents an improvement of 1.9 over method A and 1.8 over method B. With method C, we generated also more exploits than with the 2 other methods. Here is the Venn diagram of the results, and we can see that most of the flows that were validated by method A or B were also validated with method C. In addition, 846 flows could be validated only with method C, which affirmed the hypothesis advanced before. So, in conclusion, this work presented a novel method for exploiting client-side cross-site scripting, considering only the location sources. This method presents an improvement over the two previous exploits generation techniques by factors of 1.9 and 1.8 respectively. By combining these three methods, 48.3% of the relevant flows could be successfully exploited. And this explains the reason why cross-site scripting is always present as one of the most critical web application security risks. If you want further information, you can read our paper on this topic or reach to us directly. Thank you.